Okay, so all this stuff with entropy seems, really theoretical. You probably had to pause the videos quite a bit to understand it, and maybe you still don't really understand it. So while it's interesting, as long as you don't really have to answer any questions on exams that are theoretical, who cares, right? So is there any practical use for this property? Well, that's what I'm going to have you do on exams, is use this property of entropy in a practical way, in a useful way, something that helps you solve problems. And before I get into how we use it, remember that enthalpy is something that was foreign to you before you began this class. Now, it may still seem somewhat foreign, but hopefully you understand that enthalpy is simply a sum of thermal energy and flow energy. And I don't know about you, but I really like heat pumps. I like air conditioners. I like things that are efficient like that, that keep me more comfortable, and yet I don't have to pay an arm and a leg for it, right? I mean, imagine I lived better than a king did 200 years ago, right? 200 years ago, there basically was not air conditioning. If the king wanted to have a nice, cool experience, maybe a glass of ice water, they had to get ice imported from, God only knows how far away, thousands of miles potentially, right? And yet today, I just plug in my refrigerator and pay a few dollars for the electricity, which is actually very cheap, and boom, I can have ice come out of my refrigerator all day long. Or, if I'm cold in the wintertime, I don't have to bother building a fire. I can turn on my heat pump. The heart of that device that makes it work is really the restrictive tube, right? The fact that when you have a saturated liquid and it's under pressure and you allow it to expand, if you choose the right liquid, you can have some of it boil off and generate a nice low temperature that can be used for making ice, that can be made for keeping your food cold, that can be used even for warming your house, because you're going to cool the outdoors in a sense. In other words, you're going to pump in thermal energy from the outdoors. This is a great thing, and understanding these, whether it's a porous plug, a capillary tube, or an adjustable valve, understanding that the enthalpy at the beginning and end are exactly equal was a very useful thing. And so enthalpy is a very useful property in in keeping us comfortable, among other things. Obviously, enthalpy is very important even in your vacuum cleaner, right? Because there's certainly flow going through your vacuum cleaner, and understanding how that flow is generated and the amount of energy required to make it happen, all these things are important in making an efficient vacuum cleaner. So what about entropy? Well, it turns out that entropy will be useful for all these other devices, just like enthalpy was useful as well in the context of our energy balances. Because all these devices work best when there's no irreversibilities, and not just friction, right? One of the reasons I had you guys make or attempt to make perpetual motion machines is so that you began to realize that most people know friction's a bad thing for engines and for motors and all these sorts of things, for mechanical things, because we live in a mechanical world and we have some intuition about friction, and we've worked against friction. We know that if we reduce friction, it makes it easier. I mean, if I move a piano, I don't want to push that piano along the ground. I'd like to put it on a dolly and let it roll, right? It's much better. So we understand that. But hopefully you understand that there are other irreversibilities besides friction that degrade the performance of all these things. And so these devices work best without irreversibilities such as friction, etc. And what we're really saying is that these devices are most efficient when they do not generate entropy, or at least when they generate the least amount of entropy possible. So entropy is a very useful thing, because if we could quantify it and figure out how much entropy each of these things generate, the one that generates the lowest entropy is the best. In fact, ideally, these systems generate no entropy. They simply convert energy without any transformation into thermal energy. You see, as soon as you transform energy into thermal energy, you have generated entropy, because that thermal energy is going to naturally spread out in an ultimate sense. There's no way to contain it forever. So these devices, in order to not generate entropy or have no entropy change, heat transfer must be zero. So if heat is transferred, then entropy will be transferred into or out of the system, and that will degrade the performance, or at least in a sense could degrade the performance. So ideally, the entering and exiting entropy of mass, for example, would be equal, or the beginning and ending entropy would be equal for each of these systems. So how do we evaluate changes in entropy? I mean, if we say we want to quantify entropy, and we've got this idea of how we might, that we can associate entropy with some reference state and therefore tabulate how much entropy a fluid has, for example. How would we evaluate changes in entropy for a system? Well, for understanding this, we're going to need an energy balance again. So let's consider a closed system where we can write a simple energy balance that says that the amount of heat transfer into this internally reversible system minus the amount of work done by this internally reversible system equals the change in energy of this system. This is just an energy balance for a closed system that we've seen many times before. Now we can write dq as TDS, and we can write the internally reversible work as PDV, because we've used these before, right? This is just boundary work and the area under the curve on the TS diagram. And we can substitute these two in for dq and dw to get rid of all of the external flows, right? Understand that the work and heat are path dependent. That's why we're using these funny looking delta symbols. But notice we're changing them for symbols and things that are properties of the system. Temperature, for example, and entropy, pressure, and volume. These are things that are properties of the system. And the only way that these equalities work is when they're internally reversible. Otherwise, the path dependence of, on Q and W, the heat and the work, are something that have to be taken into account. But if it's internally reversible, then that's not the case. And we can substitute TDS and PDV for the work and heat terms. And so we can write it as TDS equals du plus PDV. Notice I've done something here. I've moved the work term to the other side and replaced it with PDV all in one step. So if you're comparing the energy balance at the top with the TDS equation, there's a reason I've written it as TDS, but I've moved the work term essentially to the other side. Okay, so we can write it this way, or we can write it on a per unit mass basis where we have the entropy as a lowercase entropy, in other words, a per unit mass. Same thing with the internal energy and the volume. Now, this is getting to be quite long, so to wake you up, I'm going to give you one of my corny jokes. I call this the tedious equation, right? The TDS. I know, bad dad joke, but maybe you're awake now. So we're going to call this the tedious equation because it's getting to be really tedious. Now, it turns out that this equation will work for an open system just as well, but don't worry about that. I'm not going to prove it. Just take it on faith at this point. Hopefully it won't be too tedious. Now we can do one other interesting thing. Remember that enthalpy is equal to U plus PV, or in other words, internal energy plus flow energy. And so if we were to write this in differential form, we could write dH equals du plus PDV plus VdP. Remember, you've got a product there, P and V, and so from calculus, if you take the differential, you've got to hold one constant, take the differential of the second, differentiate the first, holding the second constant. So we get three terms on the right-hand side taking the differential of this. Now, we note that dH then is TDS plus VdP because think about it. We've got something in the differential form of the enthalpy definition that looks a lot like what we had for du. As a matter of fact, notice that we've got du in the TDS equation, TDS equals du plus PDV, and that du plus PDV could simply be TDS, right? And so then a little bit of, well, actually just copying onto the next line, all I've done is replace du plus PDV with dH. And then we can rearrange this to solve for TDS again and get a second tedious equation, dH minus VdP. Now, all that's great, and if you understand it, that's fine. If you don't worry about it. What we're going to do is take both of these equations and divide through by the temperature T. Now, remember, the temperature is the temperature at which the heat transfer occurs, and it could vary as the system, if it's a closed system, as the gases expand or compress, the temperature of those gases could change, and so the temperature at which heat transfer occurs could vary, right? So these are differential equations. In the same way, as a gas or a liquid or whatever it is moves through a control volume, whether it's a compressor, a pump, or whatever it may be, the amount of entropy in that mass could change as well from inlet to exit. So we'd have to integrate through the open system, okay? Anyway, all that aside, we end up with two equations that allow us to represent changes in entropy with changes in other things that make a little more sense. Things that are maybe a little closer to being measured, like temperature, pressure, volume, right? And internal energy and even enthalpy. These are things that you may not be able to measure energy and enthalpy directly, but we're a lot closer to that than measuring entropy directly. So we're writing some properties in terms of others, which should make sense to you because, properties are related to each other. We've already seen this, right? If you look in the back of your book at property tables, the whole point of those tables is that these properties are related to each other. If you look in the saturated tables, you really only need one property to read off the rest. If you look in superheated tables, you only need two. Usually we use pressure and temperature, and you can look up anything, specific volume, enthalpy, internal energy, entropy. All these things are things that you can look up. So these properties are all related to each other, and finally we've derived an equation that relates entropy to all the other things, or at least changes in other properties.